Good morning, boys and girls. Now, today we are going to see the specific resistance. Now, specific resistance means what? Resistance which has separate or different identity. Hence, we say that it is a specific resistance. Now, generally we have dealt with carbon resistor. Now here, when I want to see the specific resistance, I have to take into consideration a particular temperature. Now when I say that particular temperature, it is expected that that temperature of that resistance should remain normal when the current flows through that resistance. The resistance of the conductor also depends upon the nature of the material used in that. Second part is that area of cross section is also very essential. Means first nature, second area of cross section, and third is the length. Now if we go and take into consideration all these 3 points, here the nature of the material cannot be given separate notation, and hence we say that two things are very much important for us. One is the area of cross section and other is the length of the wire. Now if you take a steel bar, you know that the area of cross section which you are using in the construction purpose, those steel bars, they are having area of cross section of big diameter, and if we make use of it that as a resistance, then it cannot allow the current to pass through it at a long distance, because maximum consumption will be done by the area of cross section. Next is the length. Suppose our domestic cables or the wires which we are using in the household circuit, in that case also, if we take around 10-meter wire and to other end, if I connect LED lamp, and from the other end if I give the power supply of 1.5 volt or maybe 3 volt, we find the observation that the light, the LED is not getting lighted. Why? Because here also the resistance of the wire is increased. So looking into these two examples, we have to take into consideration that while preparing a specific resistance, this area of cross section is taken into consideration and length also. So here we are putting into the equation form. You see that once I say that R is proportional to L, resistance is proportional to the length of the wire. Second is that R is inversely proportional to area of cross section of that wire. And if I put equation 1 and 2 together, I get a new equation by replacing the constant of proportionality by rho. And this rho, which is the constant of proportionality, is called as resistivity. Now if you look into the equation 3, we get R is equal to rho L upon A. But we want to find the resistivity formula. So rearranging this term, equation 3, we get rho is equal to RA upon L. Now here R is measured in terms of ohm, area is measured in terms of meter square, and in the denominator length is given, that is also measured in length. So the term common on both the sides, up and down, or numerator or denominator, is meter. So one term of meter get cancelled, and we get SI unit is equal to ohm meter. Now here, now we want to see, because now the task of that resistivity is over now. Now we want to focus on the new point, that is variation of resistance with respect to temperature, because it is very important for us, because our design of the resistance should be long lasting. It should not burn away, it should not, its property should not get disturbed. So here now we are seeing that resistivity of the material varies with the temperature. Definitely. Now if we human being also in the summer season, we know that what happens to us, that as the sun goes up in the time range between 1 to 2, and if we are outside or on the field, we find that our body temperature becomes high, we feel uncomfortable. But if we come and sit into the AC room, then that time that comfort is very, very delighting for us. So hence, in this case also, we are going to see what are the variations when resistance is considered with respect to temperature. Now here, if we take the copper material regarding the graph, resistive versus temperature, which is in terms of Kelvin, so rho versus K, we find that rho is equal to rho 0 in the bracket 1 plus alpha T minus T0, which is called as the equation number 1. Now what is there? Why it is written like this? So here when we take the graph, we are considering initial condition and final condition. When we are saying initial condition and final condition, we come to the conclusion that T0 is chosen as the reference temperature, maybe 0 degree. Correspondingly, the resistivity at the chosen temperature is taken as rho 0, and hence rho is equal to rho 0 into 1 plus alpha into T minus T0. Now, here already it has been mentioned that T0 can be 0 degree Celsius, but when it is the temperature at 0 degree Celsius, this equation number 1, if we rearrange it, we find that alpha, if I make rearrangement, I find that alpha comes out to be rho minus rho 0 upon rho into T minus T0. Now, it is very simple now. You see that rho 0 into 1 is what? Rho 0. Rho 0 into alpha, rho 0 bracket term, T minus T0. Now, this rho 0 term multiplied by 1 will be on the left hand side, it will come out to be minus. So, rho minus rho 0. Remainder is what? Alpha into T minus T0, rho 0. That rho 0 and T minus T0 bracket, it comes under this. This is called the resistivity equation, and alpha is called as the temperature coefficient of resistance. Now I have written in the form of specific resistance. If I want to write this same equation in term of common resistance, then only the thing is that you replace rho by R. Everything will be the same, and therefore we get a new equation, R minus R0 upon R0 into T minus T0. We call this equation 1, and this alpha is called as temperature coefficient of resistance. So this is how we have come to the conclusion. Now the graph for this will be like this only. They have taken the temperature on the x-axis, resistivity value on the y-axis. Now we are going to see the TCR definition. TCR means what? Alpha. Alpha means temperature coefficient of resistance. Definition. It is very simple. Actually, that formula which we have derived was that R is equal to what? R0. That equation, alpha is equal to R0 upon rho 0, R0 into that term here which we have shown you. This equation, R minus R0 upon R0 into T minus T0. On this point, we are going to see how we can define that definition. So here, if you look, when we say R minus R0 means what? Resistance per unit original resistance at the chosen temperature per degree rise in temperature. What is said? Temperature coefficient of resistance. It is nothing but the increase in resistance. Means how it is going to increase? It is going to increase because we are taking first temperature as a chosen temperature, which is 0 degrees Celsius, and after the experiment, while doing the experiment, we change this final condition, and therefore we say that this R is the final condition of the resistance, or rho is called as the final value of specific resistance. Now this R minus R0 or rho minus rho 0, that is known as resistance per unit original resistance, and this is taken at the chosen temperature, and per degree rise in temperature, that is T minus T0, is called as the per degree rise in temperature. So simple it is. So if you see the unit, and if you put the units in the alpha equation, we get, after calculating per degree Celsius or per degree Kelvin, from equation 2 which we have seen earlier, we have got that R is equal to R0 into bracket 1 plus T minus T0 bracket. Now this equation is called as number 3. Now for small temperature difference, now what we have seen, rho minus rho 0, We have seen t minus t0. Now I want to sum up this, and when I want to sum up this, my alpha comes out to be 1 upon r0. dr means what? R minus r0. dt means what? T minus t0. So a new equation is taking place. Alpha is equal to 1 upon r0 into dr by dt. So this was all about the temperature coefficient of resistance. Now here we are going to see a new point that is known as electromotive force. What is exactly electromotive force? We many times came across the word EMF, which is a short for electromotive force. Now this electromotive force, how we are going to define it? We are going to define it as, now here if you look, a circuit is being drawn here. Now I will shift this little. Now you will come to know that. You see, this is the same as Ohm's law circuit. Here we are going to take one resistance. Here EMF we are going to take it. It is having its own internal resistance, and due to the switch on condition, the current starts flowing through this resistance, and it comes and enters the EMF battery or a source, and then again it goes on rotating. Now here when we say that, what is the definition of electromotive force? It is very simple. It is defined as the energy per unit electric charge. Energy per unit electric charge. Supplied by whom? Supplied by this energy source, that is called as EMF or battery, to move the charge through one complete cycle. Means you are going to move the charge through one complete cycle. And all this process which is done by the help of this battery, that is called as the electromotive force. So this is the definition of this. Now we are going to consider some explanation about this. Now you see that first of all circuit. Now you have seen the simple circuit of Ohm's law. One resistance across the battery is connected and the current flows through it. Now this circuit is having one EMF device and one resistance. Simple. Next is that if you see the device is EMF device has two terminals. One terminal is a positive terminal which is said to be at a higher electric potential. Then there is another terminal that is called as the negative terminal, which is at a lower potential. EMF, how it is working is represented by the arrow which you have seen earlier. It is the arrow which is showing from the negative terminal to the positive terminal of the device. Means the charges which are going to be moving in the circuit. It is found that in EMF it is traveling from the negative terminal to the positive terminal of the device. When the circuit is open, means now we are considering that we are using a key for this circuit. When the key is pressed, this cycle takes place. But when we say that when the switch is open, that time we say that it is switch off. When it is said to be switch off, then there is no net flow of charge carrier within the device. When the closed circuit or the circuit is closed, we say that there is a flow of charge carriers. from one terminal to the another terminal. Means here movement is seen, and this movement is due to the region of EMF device. So the positive charge carrier moves toward the terminal which acts as a cathode. That is negative terminal, we call it, inside the EMF device. Now, does positive charge carrier move from region of lower potential to the region of higher potential energy, which is captured inside the EMF device? Yes, the positive charge move from, because when the charge is being driven throughout the one's complete cycle, that time its energy goes low, and then when it enters it achieves the energy, and therefore we say that it flows from or moves from lower potential energy to the region of higher potential energy.